Okay, thanks. Okay. Thank you, Ravi, for the intro. And first of all, I thank this field. So I work in the soft condensed matter laboratory, which is a research group headed by Professor Alberto Fernandez Nieves. He is so we are based in Georgia Tech Atlanta School of Physics, and for the past 2 years we have been also setting up a lab in University of Barcelona, thanks to a collaboration between the departments. So I spend my research time in US and Spain. So currently I have been stuck in Spain since 1.5 years. So not stuck. Stuck is not the right word. I quite like it here. But yeah. So so before I begin, I would like to thank Alberto and all my collaborators and group members for whatever work that has gone into this, my own work as well as my understanding of this field. So this would be the outline of the talk. So at any point, if you have any questions, so I cannot see the chat right now. So maybe if there is some issue, maybe Ravikiran or someone else can unmute themselves and tell me either to slow down or if something is not working. Okay. So this would be the outline of the talk. Yeah, sure. Okay, thank you. If you are interested in 2D, 3D, and basically, you have a crystal lattice, you define the Bravais lattice, you have the basis and the structure and everything, and any imperfection or anything which is off place in the slight sense of the word can be called a defect. And there is a whole industry, mainly semiconductor and material science fields, which have made their living out of studying defects and how we can engineer defects into our daily use. So that is perhaps the most familiar example of defect. So you can see some of them here. You can have an edge dislocation, you have a disclination, or you have some twist in the lattice. So these are classical examples of defects in condensed matter physics, which you can find in any of your textbooks. Certain other examples, if you are someone into optics and looking at polarization fields, if you look at the the polarization field of sun or any star on the heliosphere, you will actually encounter singularities in the polarization fields, and which are, at least visually, they are quite region being a very generic word in whatever dimensionality you are talking about, where this particular order or the order parameter is undefined. So we'll work with that definition here. Okay. So let's focus on this example here, liquid crystal, because it's very colorful and it's very instructive. So liquid crystals are systems which are literally between liquids and crystals. So when you have a crystal, you have, your broken symmetries and you have translational order along some axis and also orientational order in some other axis. And as you melt the crystal, either by using temperature or some other control parameter, you end up with an isotropic fluid, which which is known as a liquid state, characterized by the absence of any orientational order or positional order. So whichever way you look, the system is isotropic. So in between the liquid and the crystal, you have these different, exciting exotic phases known as liquid crystals, which are characterized by certain symmetries being broken, but not all of them. So in this case, this would be the phase, the pneumatic phase, characterized by N would be the phase which we would be focusing in this talk, where these rod-like constant particles are aligned in one direction. So there is some sort of an orientational order, but there is no positional order. So if you translate this phase by some amount in any direction, it looks the same. But if you change the orientation with respect to this axis, which is known as the pneumatic director, which is our principal axis, one of the principal axis, there is actually a difference in the system. So temperature is only the only control parameter. So if your liquid crystals are temperature sensitive, they have lyotropic crystals and chromonic crystals as well. So quantifying some of the parameters. So like I said, in order to define defects, it's the best way to define is using an order parameter. So you have these particles, and when they are randomly aligned, you calculate the quantify the field by using the angle between each of the constant particle and one of the axis, whichever axis of your choice. And once you average it around the isotropic phase, you will get a net alignment which is 0. But when you're aligned along the axis, so again, the other key feature of pneumatic is these particles are head-tail symmetric. So if I'm oriented at 0 degree or pi, it's the same. So there is a 180 degree rotational invariance. So using this angle theta here, so these go into these unit vectors called u hats. And with that u hat, you can construct an outer product and make it traceless and everything. So we are talking the simplest example in 2 dimensions, but this can be extended to 3D as well. You construct this tensor, which is your pneumatic tensor order. And once you diagonalize this tensor, you can get a scalar out of it and a vector field out of it. So this scalar is our pneumatic order parameter. And this pneumatic director field is what defines the underlying liquid crystal. Okay. So we only need these 2 parameters to completely know everything about our system. So wherever this order parameter is undefined, you can call that region as a defect. It's as simple as that. Simply put, defects are signatures of liquid crystalline systems. And so these lines, they correspond to this N field, this pneumatic director field. So discrete particles, but when you make it continuous, they look like that. So at these locations, you are unable to specify any local point, and hence that point would classify as a point defect in such configurations. So we quantify defects in such systems or in physics in general using what is known as the topological charge. And this, at least to some of you, might ring a bell. This you might have encountered such a formulation in your complex analysis methods as your residue or your winding number. So here the d theta is your infinitesimal change in the orientation angle across the field. And as you go around a point in a closed contour specified by C, you calculate how much of the total angle it changes, and that quantified parameter is what is known as a topological charge. So in the case of head-tail symmetric particles, we have half integer disclinations or half integer defects. So the plus and negative sign are actually coming from the exact calculation of this. So throughout this talk, I will try to make parallels to some of the topics which you might be taking in your BSMS physics courses, so that things fall into place. So this is actually the winding number, topological charge. It appears by different names in different contexts. So a different charge defect. So this one is a plus half. So the plus half has a very distinctive comet-like shape, and under a polarized microscope, it looks like that. So the minus one half has threefold rotational symmetry. So the plus one is when you have a defect and you go around it 360 degrees and you end up in the same configuration. So that's perhaps easiest to imagine. The minus one halves, and some of these vector fields actually correspond to some of the fields that you solve in your math methods or IDC courses, your divergence and curl fields. So there is parallels between that as well. So how exactly we calculate the topological charge? Just by a simple example here. So imagine a matchstick which is actually head tail asymmetric. So there is a head and a tail, and you move this matchstick or pin or whatever along the director field, and when I go in a contour by 2 pi degrees, I end up in the same configuration. So this measure is 2 pi, so 2 pi or 2 pi is plus 1. But when I translate it along the director field around this defect, I actually end up with the opposite configuration when I go 2 pi. And it is opposite in the sense that I have to invert it by minus plus everything that is pi over 2 pi, and that is a plus half. And in the similar way, I have to go clockwise when I go counterclockwise in the contour, and this is the minus 1 half. So this you can find not just in liquid crystals everywhere. So if you all look at your finger, you can actually find your fingerprints forming plus 1 half and minus 1 half defects somewhere along the line. Not quite clear here with my finger, but pretty sure you can find it among us. And these are the simplest defects, but there are highly exotic defects as well, defects and defect systems. So for example, you can have defects in the bulk of a liquid crystal or other systems, and they can evolve with time. So this defect here starts out at the surface, which is known as a Boujum, and then they split into two, moving equatorially, forming some sort of a Saturn ring. So this is known as Saturn ring effect in liquid crystals. And you have other kinds of defects like Boujums and disclination, and these what I have talked about are 1D defects and things like that. But you can have defects in the bulk, which when you look from just projected just onto one plane, they look at point defects, but they are actually through the surface. So funny story about how this name Boujum came into being. So this was actually coined by Professor Mermin. Singularities or your zeros of your vector field or your analytical field that you define, right? So these are things which you can calculate. And chi is a purely topological object. So it is not object. So this is actually a very strong connection between something which is analytically derived and something which is topologically derived. So, that is a very strong connection between two distinct branches of math through physics. So this is actually the fundamental constraint that topology puts on physical systems. So winding it all back to where I started, that is liquid crystals. So you have this ordered arrangement of particles in. So this is actually a defect-free alignment in 2 dimensions. So you can comb these particles in a straight line, and there are no defects in this system. And this is actually the least energy configuration in 2 dimension in flat space. But as soon as I put these particles on a sphere or any other different object with a different topology, then defects are actually predicted and actually demanded by the topological constraints. So these have been predicted in theory. So you have this sort of a baseball configuration if you try to align these particles on a sphere, where you have defects at the 4 corners of a tetrahedron. And everywhere else you can actually smoothly vary this director field. Okay, and these were predicted in the 90s and 2000s in the context of liquid crystals and other systems, and they were experimentally observed towards the starting of this decade in liquid crystal systems. So this is actually a liquid crystal shell in which viewed under polarized microscopy, where you are able to locate the defects in steady state when they move and assemble at the vertices of a tetrahedron. So again, trying to connect these things with something which you already know. Again, this is the perfect defect-free alignment of particles in 2-dimension flat space. You can have 2 configurations of these things, in theory, like you have the poles on the earth, the north pole and south pole, and you have things aligned as longitudes. But at this point, you cannot put a particle there and specify an alignment. It has to come out of the surface. Or you can have them aligned as latitudes, but still you would end up with two defects at the north pole and south pole. You can have more defects, of course, but these are the least energy configuration if the particles are polar. So if they are head-tail asymmetric. If they are non-polar, if they are symmetric, then you so these are +1 defects. So connecting this back to the index theorem here. So I said here that the convex polyhedra have an Euler cavity. So all these are connected to the sphere. And you know the Poincare-Hopf theorem. So you have the +2 here on the right hand side. And you see here that the north pole is a +1 defect and the south pole is a +1 defect, and 1 + 1 is 2. So the Hopf theorem, index theorem is satisfied here. But 1 + 1 is not the only way in which you can get to, right? You can have 4 times plus halves if the particles are allow nematic symmetry. And that's what you observe as a baseball configuration if you have particles which are, head-tail asymmetric. And these have connection to, this is something that, Thomson problems or chemistry courses or in your +2 or somewhere you might have learned about the VSEPR theory, right? Valence, shell, electron, pair, repulsion, something. Yeah. So these were actually a set of problems proposed by J.J. Thomson in which he was asking questions like, if you have 2 electrons on a shell, what is the least energy configuration that they have? So if you have 2, they have to be at the poles. If you have 3, they are at 120 degree on an equatorial plane. And if you have 4, you have mass at tetrahedron and things like that. So these are some beautiful connections between, hard condensed matter systems and, liquid crystal systems on this context. So that is how, even though you can have, there is no requirement for defects to present the ground state of a system, topology can force them to be present in a defect. So there is no defect free state if you impose these topological constraint on a system. Now bringing on to the other aspect of this talk, which is active matter. So far I have been talking about systems which are passive or which are driven in that sense. So what do you mean by active matter or activity in this sense? So activity directly corresponds to a system being non-equilibrium. So what I mean by that is, it is not possible to define these systems from the framework of equilibrium statistical mechanics or thermodynamics. So each of these systems, very broadly speaking, they are characterized by energy input at a single particle level. So each of the particles have access to the energy and they dissipate the energy in their own way. So it is unlike, your equilibrium stat mech examples, like where you have a thermal bath of sorts and the system equilibrates first, and then by finding out the mean temperature and the fluctuations about the mean temperature, you can quantify, you can calculate, the free energy, the entropy, and you can know anything and everything that you need to know about the system. But in this case, the energy input is at the single particle level. So there is no equilibrating with a, a sink or anything of that sort. The whole system goes out of equilibrium. So that is sort of the broad picture of what you need to keep in mind when we talk about active matter. And looking at examples of active matter, we are active matter. So we as living systems, our life is a struggle against equilibrating to, monotony or what. Okay, that is a bit philosophical, but still, if you look at a cellular level or if you look at an organism point of level, if we equilibrate anything and everything to our surroundings, we just die. So there has to be gradients maintained, there has to be flow and transport maintained, there has to be emergent phenomena. And the way to achieve all that is to stay in equilibrium and stay active. So active is in a very literal sense as well as, in a much more deeper sense. So some of the examples of active matter systems which have been in study in the past 10 to 20 years. So you have these system of granular rods. So you can imagine these things as like the liquid crystal individual molecules when they are vibrated in a closed container. they so each of these is a random walker, so they have a persistence length, but when you try to look at the collective dynamics of these things, they exhibit something known as number fluctuations and density fluctuations. So in equilibrium systems, the number fluctuations go as square root of n, but in active systems where each particle can dissipate the energy on its own, they display fluctuations which are higher. The exponent is higher than 1, so they fluctuate at a degree which is greater than that of equilibrium systems, and that is a very unique signature of active matter systems. Other parts are like you can have these chemically synthesized Janus particles, so which are like surface treated. So one surface is say like hydrophilic and one can be hydrophobic, or one is responsive to electric field, one is not, and things like that. So under similar electric field, depending upon volume fraction or varying other parameter, the same system can behave as either as a real gas, or as some sort of a quasi-ordered lattice, or as long chains, or as a phase separated solid and a fluid medium. So this is the same system behaving under electric field, so but not driven. So the electric field is not driving the particles to one direction, but they are able to sort of self-assemble into different structures based on the fact that they are active. The other key examples of active systems, almost all active systems, like I said, are found in the living world. So here you see this is work from my own group, done by not done by me. This is a certain other project which is going on in our group, where you can do ant aggregation. So these are ants, and collectively they can behave as a solid. So they have some sort of a elastic modulus and a rigid modulus, bulk modulus, as you can see here. So when you try to force them, they actually resist the force and they can retain back to their shape. But when you confine them into a much broader vessel and you put an object, they can behave as a viscous fluid as well. So this is the classic ball dropping through a viscous fluid experiment done with ants. So they have viscoelastic properties, and this is an inherent this is an emergent phenomenon which comes out of the fact that these things are active. So each ant is consuming its food and behaving on its own, as well as they have a collective behavior as well. And speaking of collective behavior in natural world, most beautiful examples are fish swarms and bird flocks or starlings, where these things in order to escape a predator, or in a better way to consume food or something like that, they form these large swarms or schools, or randomly moving flocks in nature. So these are just some visually appealing examples of active matter which I handpicked. So in all these examples, you can see that the detail balance is broken at a single particle level. So the system is inherently non-equilibrium. Also define defects in such systems. So how, as an example of defects in active matter system, I would like to introduce. Okay, why is so this is the combination of everything that I have talked about so far. It is activity and pneumatic crystals, and this is the broad area which my research happens. So you have activity, which is energy input at a single particle level, and you have pneumatic liquid crystal systems. So you know that defects can be imposed in liquid crystal systems, but what fun things can we do when you also make those particles active? So the intersection of this field is has been very exciting for the past 5 to 10 years in soft condensed matter physics, and this is actually the experimental system with which I work. And before I play the video, I would like to on the fact that you can actually see the +1/2 defect, a comet, a C-shaped defect here and here. I hope you can see my cursor, and you can see the threefold rotationally symmetric -1/2. These triangles here, over here, over here, over here, and things like that. So the cool thing about active systems, as you can see in some of these examples, is that these things have some sort of a self-propelled motion or self-assembled motion or thing of sorts. So whereas in the case of passive liquid crystals, unless you force an external field, they don't move. So these things do move, and what that means is that the defects in such systems can also move, and that itself is exciting because your defects in your conventional condensed matter system, in the case of a crystal point defect, it is static. And so when you have moving defects, it's a whole different exciting field, right? So let me try to play this video here. Can anyone confirm if they can see the video?
Yes, it is visible.
Yeah. Okay, I'll play. So you see that the defects are moving, the whole system is moving, and you can see defects forming, creating, getting annihilated, and things like that. The key thing here is, here you can see that this is a two-dimensional object. So this is so if you go by topology doesn't require anything to be any defects to be present in flat space. So like I said, if you have these long fibers or whatever you have, you can have a defect free state as your least energy configuration, but still we have defects here, and that is purely due to the fact that this system is active. So if this system was passive, everything would relax into a state where you have nodes and everything is perfectly aligned in as straight parallel fibers. But here defects are getting created and they are moving, and here you can see a plus 1/2 created here, a minus, and they are moving away. So it's quite an exciting system, and here you can see that they are joining and annihilating into nothing. Here also they are getting, the fibers are straightening out, but earlier there were two defects to begin with there. So plus 1/2 minus 1/2 together they form 0 because the math checks out, right? So that's the thing. So topology says that there is no need for the system to have defects, but activity demands that you need to have defects. And again, we satisfy the Poincaré-Hopf theorem. So if you quantify these defects in this, you have an equal number of plus 1/2 and minus 1/2, so that when you do the index theorem and you sum it all over, you still have an Euler characteristic of 0, which is your global topological constraint. So that's the beauty of it. You have a mathematical concept, and your physical experimental system satisfies it, but in a very aesthetic way. And these things are enticing to look at. So you can guess how easily I can spend time in the lab. So the natural question is, okay, you talked about all these things. So first of all, what is this thing? So I'll just give a very brief idea of what this system actually is. So this is actually a biophysical system made up of microtubules and kinesin. So these are proteins found in our body. So the long fibers that you see are actually bundles of these microtubules, which are actually long proteins which are inside our cells, which form our cytoskeletal network. So these are the roads on which, I'm pretty sure you might have seen this video somewhere in your intro bio courses, where these little kinesin proteins walk on these fibers, transporting vesicles or cargo or things like that. I had the video, but like I said, the videos aren't playing, so I removed it. So the system that you just saw is actually a modified form of that system. So this is not an in vivo system. This is not living. This is actually taken out of the cells. So you have these microtubules which resemble the long elongated molecules in the liquid crystals, hence the entire introduction about liquid crystals. And you have these proteins which walk between them, causing relative motion. So all the sliding and breaking and bundling up of the things that you saw in the video is due to the fact that these protein molecules, they use ATP. So ATP is our energy currency, as always, in between these fibers and causing them to move and buckle and break. Okay. And what you see here, so one line that you see here are actually thousands of these protein molecules bundled together. So in order to give you some size of the system, this picture is actually a 1 by 1 millimeter. So this is actually 1 millimeter square in area, or maybe a bit less, but we make these conveniently skip that part for now. So this is actually an orientation correlation function. What this means is that I take defects 2 at a time. So here positive defects, and I ask the question, if my 2 defects are at a distance r, separated by a distance r, how correlated are they in the direction? Are they both pointed in the same direction? Are they pointed in the opposite direction? Are they orthogonal, or things like that? If they are in the same direction, this function gives me 1. If they are opposite, it gives me -1. If they are orthogonal, it gives me 0. So this is actually a projection of one orientation onto another at bin by distance. That's all this is. And the x-axis is actually the scale distance r with r0. So r0 is our relevant length scale in the system, which is calculated from the mean defect spacing. So when you have a system of defects and you can quantify their positions, you can calculate the defect density over an area, and inverse square root of that gives you the mean defect spacing. So that is your one length scale in your system. So when my 2 positive defects are far apart, that is at r greater than r0, there is no restriction by topology or activity that they should be aligned or anti-aligned or any direction. So when I take a huge number, thousands and thousands of such examples where, say, like my 2 defects are at a distance which is 4 times the mean defect spacing, any random alignment is possible. So when I bin it over a distance random vectors and you average over the orientation of random vectors, and you get a 0. So this is your equilibrium measurement, and we get that. But when the defects come closer and closer, you know that these are topological defects by the director field. And the director field is by the local alignment of the fibers itself. And you know that how they bend and buckle and go all that. So when you are in a region where these defects are in very close proximity to each other, they actually feel the force and the torque. So they can no longer take any random alignment. And so they develop this of anti-correlations, because these are positive defects. So circle, right? And you can see that this is a schematic in which, and you see that this +1/2 at the -1/2 very close. So in the next frame, these two join together to give you a 0. So they just annihilate. So that's cool. And the entire picture looks like, you have this nice, characteristic shape, and the different colored lines here correspond to different experiments with different defect densities. So regardless of the defect density, when I scale with the relevant length scale in the system, which manifests from the defect density, the qualitative feature is constant. And this has been verified by simulations as well. And this is the recent work which has been published. So that is a bit about my work in 2D flat space. And in the interest of time, I will end the talk just by introducing another concept which hopefully would increase your curiosity a bit more about these things. So remember, I talked about topology, right? And the Poincare-Hopf theorem, and how it globally puts a constraint on the system. So from whatever I talked about right now, all it says is that, okay, if I have chi which is 0 or even non-zero, the topology says that the sum of all the charges should equate to chi. That's all it says. It doesn't say how these charges should be distributed. It doesn't say how many charges have to be there. It doesn't say anything about the microscopics or the specifics. So in that sense, topology puts a global constraint on the system and not a local one. And that is what has been verified in theory and experiments. But the local constraint in this system is specified by the geometry. So when we talk about geometry, and again, the examples which I have showed and the results I have showed is in perfect 2D flat space. So there is no notion of any curvature there. But you can have curved spaces. You pick a paper and fold it, and you have a curved space, and you can quantify the curved space by, the tangential oscillating circle at that point. So these are, your geodesics on the surface and the radius of curvature associated with each point, and the tangent and the normal vector associated with each point. So you can quantify the normal curvature, the mean curvature, and the Gaussian curvature. So these are standard mathematical definitions of quantifying the local geometry of any line, right? So in this case, if you have a saddle like this, you have a line of, these are two the principal curvatures, one with the maximal curvature and one with the minimal curvature. So the average of that gives you a mean extrinsic curvature, and the product of that gives you a Gaussian, the convolution of that gives you a Gaussian curvature. And this is your local constraint on the system. And that is beautifully correlated with everything else by the Gauss-Bonnet theorem, which connects the local geometrical aspects to the global topological aspects. So the left-hand side of this theorem is your Poincaré-Hopf theorem, which we have been talking about throughout so far. So you have the Euler characteristic chi, you have the sum of all the singularities, and this is the global topological constraint. But locally, once you have the Gaussian curvature over the surface of interest, and this need not be a two-dimensional surface, this can be the 2D surface of a curved 3D object or higher dimensions as well. So you have to, calculate the integral appropriately. And you see that the local geometry defines how exactly this sum happens connects to the defects as well as the Euler characteristic. So that's the beauty of Gauss-Bonnet. And as instructive examples of Gaussian curvature, if you have a saddle, you have one of the K1 is positive, one of it is negative. So the product would obviously be negative. Curvature. If you have a cylinder, so at the surface of a cylinder, you have a straight line. So the radius of that circle is infinite. So the curvature is 0. So product of the Gaussian curvature at this point is actually 0, because no matter what the other curvature is, this one is 0, right? And if you have a familiar example of a sphere, you have two positive curvatures. So when you do this integral with appropriate dimensions, you actually get this integral relates to 4 pi, and 4 pi over 2 pi is plus 2, which is actually the topological Euler characteristic of a sphere, and which is actually what we obtain by the sum of defects as well. So I hope that connects everything that we have talked about, right? So that is how locally at each point, if you know the Gaussian curvature, you know what is the local constraint on our system. So some exciting surfaces or systems to study the effect of the local geometry is a torus. So toroidal surfaces are extremely beautiful because in one single system, you have all three curvatures possible. So you have an outside surface which is positive. So this is like a sphere. You have an inside surface which is like hyperboloid, or which is like a saddle. So these are negative. And you have two central rings on the top and on the bottom, which are exactly k equal to 0 rings. So in the same, you can achieve all three Gaussian curvatures, as this Gaussian curvatures varies smoothly when you traverse along any theta hat or phi hat. So you have access to the entire range of curvatures in one single system. Also, the Euler characteristic of a torus is 0. So topologically speaking, the torus is very similar to infinite flat space because they both have chi equal to 0. So what this means is that if I put defects on this surface, topology says, okay, we don't need any defects, or rather we need equal number of positive and negative defects. But curvature, since it is non-constant and varying throughout the surface, it can have different effects on different kinds of defects. So this was again predicted by theory and then later observed in experiments and quantified in experiments in our group, where you have if you put the same active pneumatic system on a torus, which is what I do for a living, you have defects separating and unbinding induced by curvature, because here, unlike the case of a flat space, you have a field of the curvature. So the geometry is different. So all your differential equations, they have to carry the metric of the local surface. And that dictates how the defects move, what are the geodesics, whether elasticity dominates or the, whether, let's say, the geodesic given by the minimal solution would be the one taken because of energetic reasons, or whether the defects would annihilate before they complete the journey across the geodesic, and all sorts of exciting questions like that. So the other key question is, how do you make a torus, right? So since these are fluids, you know that by surface tension, all fluids end up being spherical, right? How do you put a hole in a fluid substance? So that is another thing which my lab has expertise in. So we make fluid droplets, toroidal droplets, or actually droplets of any shape. So we basically 3D print fluids inside fluids, depending upon whatever we need, by a very simple technique, which basically involves flowing one fluid inside another fluid. That's all it takes. So you have an inner liquid, you have an outer liquid, so you have liquids which do not mix, and you have a rotating stage. So by tuning this parameter space of this rotating velocity and the viscosities of these fluids, you can actually achieve a regime in which the surface tension can be surpassed and the fluids remain toroidal, or any shape that you want. So this is actually prior work done in my lab at the earlier part of this decade or even before, in which you create toroidal droplets, and since they are unstable, since surface tension dominates, they end up being spheres. So depending upon their aspect ratio, the length scales in a toroid, they can either shrink to a single sphere or they can break into multiple droplets. And this should remind you of your Bohr's model of atom, right? Depending upon wavelengths you can accommodate in this 2 pi ring, it quantizes and breaks up into a number of droplets based on how many wavelengths it can accommodate. So these are actually hydrodynamic instability. So this is actually classic fluid dynamics. This is known as a Rayleigh-Plateau breakup. So what we need is, so actually I should be playing the movie, but yeah, let me try quickly to show you how we make this. So this is actually the needle through which the inner fluid flows. So this is actually an oil bath in which a water-based fluid is flown. Okay. And you see the fluid is flown and it makes a perfect toroid. And when you stop the flow, now the video is stopped. So you get a perfect torus of the fluid, and it still has not broken up into a sphere. Okay. But eventually it does break up into a sphere. So here you see, as time passes, you see this shrinking and this swelling here. And since this accommodates 3 wavelengths, it breaks up into 3 spherical droplets due to surface tension. So that's cool, but that is of no use to us. We need to stabilize this thing, right? So we have done that as well. So what we use is actually a yield stress medium. So these are non-Newtonian fluids which can support stress. So when you actually try to shear the fluid, they actually behave as a fluid. But when the force or the strain that you put is less than this threshold, it actually behaves as an elastic solid. So non-Newtonian fluids, the classic examples that you might have been familiar is your cornstarch experiment, which you do in your Anvesha, demos and things for kids, right? So cornstarch, if you try to press it hard, it behaves as a very elastic solid. But when you slowly force it, you can actually sink in it. So this is actually kind of the opposite of that. This is actually a different non-Newtonian fluid. And once you have that, you can actually make the torus like this, because the outer fluid actually can hold the stress and prevent it from breaking up into individual droplets. So we actually make this medium ourselves and characterized it so that it has enough elastic moduli to support the strain from the surface tension. You can make the inner fluid as your liquid crystal. So this is again joining, combining and going back and combining everything what I have told before. So replace the inner fluid with a pneumatic liquid crystal. And then you have a torus made up of a liquid crystal. So you can have defects on the torus and you can study whatever I have said so far. So you can see that you make the torus and you can make double torus. So this object here has a Euler characteristic of 0, but this one here has -2 since it has 2 holes. And this one here has -4. This one has this another configuration of -4. So double and triple tori. So this is actually a very cheap but very beautiful way to 3D print fluids inside fluids. So, and that is something which our lab has expertise in. And instead of flowing regular pneumatic tori, if I flow these active pneumatics, we can actually, make the system active as well as pneumatic. And this is prior work done in the lab where we characterize this charge with respect to the Gaussian curvature and the topology and all these things. You can study transitions between this and this. So I make this object here. This is ongoing work in the lab actually. I make this object here with a chi equal to -2. And I force this system to change its topology. So I try to merge these droplets so that it goes from chi equal to 2 to chi equal to 0. Then it shrinks to chi equal to 2 plus 2. So the Euler characteristic changes, but the defects have to be there, right? So it's interesting to see how the defects evolve with time. So I'll end with showing one final video about this system here because it's just so cool to show. Yeah, here. So this actually actual confocal microscopy image of that active pneumatic on the torus. So this is actually how it gets imaged. This is of course false coloring. The color has nothing to do with the actual stuff. So you can see the fibers of the microtubules, the +1 halves, the -1 halves. And we image till the hemisphere because of imaging limitations. And you can look at it from different angles. They move in time like I showed in flat space. So just playing it again because it's cool. And yeah, there you have it. You have topology, you have curvature, you have activity, you have liquid crystals, everything put into 20 seconds. But of course, it takes much more time than that. So that's what I have been doing. And some exciting aspects which I have been focusing right now is to look at sound modes in these systems. So these are some theoretical predictions in which they predict that if you have these particles, active particles and defects moving in these curved geometries, they can slowly assimilate into a flock, into a steady state in which they have a band-like structure across the equator, forming second-order defects at the poles and things like that. And the waves which form in such systems are very similar to the waves which are found on the Earth oceanography. But in that case, the Earth's rotation is actually the one. Earth rotation, Coriolis forces, and other things are the ones which are leading to local confinement of waves and sound modes. So there, the waves are actually physical waves in oceans. But here, the entire sphere or the background or the substrate is not undergoing any motion. This flocking or this sound modes are created purely due to the activity and the curvature of the system. So it's a very beautiful interplay of the two things. So currently we are trying to realize this in experiments, and you have band gaps opening up due to the curvature and things like that. So as a take home, what I intended by this talk is not to talk about my personal research a lot, but to at least invoke the curiosity in your mind that topological defects are exciting, passive or active or whatever it is. They are very and unavoidable signatures of physical systems. So defects are not necessarily a bad thing per se. And in active matter, defects can behave as active particles within dynamics. They can, with their own interactions and dynamics. And they have, a wide variety of emergent behavior like, number fluctuations, collective motion, self-propulsion, flocking, and everything, which can be tuned locally by geometry and globally by topology. And like I said, as I showed for some of the theoretical examples, that is the forefront of StatMech and theoretical, one of the forefronts of theoretical physics. These can serve as a very good experimental test beds to test some of those theories as well as to observe for new exciting phenomena. And yeah, so that's basically what I had to say. Sorry, it exceeded a bit. We are a bit over 1 hour, but yeah. So I would like to end and I'd be happy to take any questions or comments. Yeah. So should I keep the presentation on or is it okay?
I think it is fine.
Okay.
So basically, you made a statement that the topology demands presence of defects.
Yeah, not always, but it can. Yeah.
Yeah, I mean, because I think we can demand the presence of defects by just entropic considerations. I mean, in
Sure.
this particular example, what exactly? I mean, here you have this theorem which says a constant. For that, so
Yeah.
I think that would the defects that are created.
Yeah.
They're created in such a manner that it is.
Yeah.
So we have corresponding antibiotics.
Yes, exactly. So yeah, that's that.
So no, but here this statement that topological is finding the presence of defects themselves, that is not.
That statement I was trying to make since I was transiting from where I was talking about the alignment of this liquid crystals on a flat space, right? So here you can have a defect-free configuration where you align all these things in a straight line along the direction.
Okay.
Right. But when I put this exact same system on a sphere with of a different topology, you cannot put the system without the presence of defect, right?
Okay. Oh, right. Okay. Okay.
So that's what I was to say. Yeah, go on.
The football analogy was in respect to this particular thing.
Analogy also works well with this thing. So, so in the football, you see that the pentagons are five. It has 5 vertices, right? So if you define a function of an order parameter of a defect there, the perfect HCP, the hexagonal arrangement, would be your defect-free state in flat space, because in flat space you can have an infinite array of hexagons and fill the space.
Okay.
But when you put the sheet of those hexagons, so if you are trying to wrap graphene on a ball, which is your C60 buckyball, right? You cannot have the C60 buckyball with just hexagons. You need to have pentagons as well, which is your soccer ball, the football again.
Right. Okay.
And on the football, the pentagon is actually a +1 defect. Not exactly a +1 defect, but it lacks one vertex.
Okay.
And in